Hey everyone, and welcome to an introduction into using R and R Studio. So by now you should have downloaded and installed both R and R Studio. R is base R, which is necessary for R Studio to run, right? So once you download and install both of them, you'll never have to download and install or never have to open R again. All you do is open up R Studio and it's going to be running base R in the background. So you should have downloaded and installed those by now. Briefly, let's go over the various windows. You can open up R and you'll see these 4 windows populate. Sometimes you'll open up R and it looks like this. So you have 3 windows, 1, 2, and 3. And why is that? What's happening here? Well, what's really happening is that you don't have a script window open yet. So you have to go here to this little box here with a plus sign and click on R script. So it's going to open up a new R script window. The keyboard shortcut, if you saw that there, is for a Mac would be Command, Shift, and N. Or for a PC, I think it's Control, Shift, N. So now we have the 4 windows. So let's go here. Briefly, let's talk about these 4 windows. These windows are important for getting work done with R. The first window is our script window. It's the upper left-hand corner. I mentioned before that when we're working with base R, the old school days was a time where you would work in R, you would close the window, and if you closed the R window, everything was gone, right? So with R Studio, which is a graphical user interface, a GUI that wraps around R, R Studio provides the script window. And in the script window, you just write all the coding that you want, right? So you don't have to input it directly into a console. What you're instead doing is like trying out code, right? So that's what that goes there. You can even write notes to yourself in there. You can try out code, block out that code or make a comment before that code. That way R won't run it, right? So you can do various things with the script window. And then when you're done, you save it. That way, next time you open up R and R Studio, you have this window here that's going to have all of your information already there, right? From here on out, every time I talk about R Studio, I'm just going to refer to it as R, but know that R itself is base R. But when I say R Studio, or when I say R, I'm referring to R Studio since we'll be working mainly in R Studio. So that was the script window. Next, we have the console window, right? So the console window is important, right? This console window is exactly what you would find if you opened up base R, right? So again, old school days, we didn't have R Studio, we just had base R, so we'd open it up, it'd say all of this stuff here, right? It just says your version, let you know it's free, let you know that a bunch of contributors participate in the R project, and then you just start typing things in here. You see this blue caret here, you just click there and you start typing things out, right? So your calculations or whatever. But in base R, you close it, that's gone, right? So the difference here with R Studio is that we don't just have this console window where the calculations happen, right? We have a bunch of different windows, right? So whereas the script window, you can write anything and nothing will happen after you write them, we have the console window, which is fully base R. The console window is where we actually run those calculations, right? So in a console window, I could write 3 plus 2, hit enter, and it will calculate it for me. In a script window, I could say 3 plus 2, hit enter, and nothing will happen, right? Because I haven't submitted it to the console, right? This is where all the magic happens down here in the console, right? But up here, we want to save the stuff before the magic happens. So, yeah, so we enter things here, it'll run the calculations, we save things here, right? we can type in 3 plus 2 here, but we'd have to run it into the console window. Next, we have the environment window. The environment window is important because, as mentioned before, the R language is based on, or is an object-oriented programming language. What that means is you can create new objects for any data set that you want to read in, any information, any calculation you want to read in. So, unlike SPSS, which only deals with one data set at a time, unlike I think SAS only deals with one data set at a time, unlike Stata, which deals with 2 data sets at a time, R can deal with hundreds, thousands of data sets at a time, right? So object-oriented programming just means that we have the ability to create new objects, new data sets, and we can work with all of them. You may have a data set that deals with crime statistics across the United States, and you may have another data set that has like demographic information based on the census. Well, you want to work with both of them and merge them together, right? In R, that's very fluid, right? So you can put both data sets into your working memory. They'll populate in your environment, and you can merge them together. In other platforms, you can't really do that. You'd have to do it by hand, or you'd have to do it one at a time. Let's say you have 3 data sets that you want to work with. You can't really do that in Stata either, right? So here, we can work with as many data sets as possible. You can even sort of tinker around with one data set, make a smaller version of that data set, put that in the working environment, and then maybe merge that into another data set, right? So this environment window will list all of the data sets or objects that you have in your working memory. We also have a history tab. It just shows you all of the commands that you've run in the past. And then finally, we have this plot/viewer window. Mine currently has a help window open. If I look at files, it'll list all my files. We have plots, so when you start plotting like maps or histograms or bar charts or anything like that, box and whisker plots, they'll populate there. And we have packages listed here. So packages that obviously we know that because R is trying to be lightweight and very easy to use, it relies on packages that are on servers elsewhere, right? Quote unquote, the cloud. So what we have to do is download those packages, then download and install those packages, and then load them into working memory. So while you're figuring out if you want to load a package into working memory, if it exists already on your computer, then you can just highlight those packages that you want. So that'll give you a list of packages, right? So let's do this here. Look at packages, and it'll list every package that exists on this machine. Right. Okay, next, getting familiar with R. Setting the working directory is very important. And that's because when, let's say you're working with a data set, or you want to find, want to read in various data sets, or you want to save data for later, R needs to know where to save those things, right? And you can tell R, hey, this is the directory or the folder that I'm working from on my computer. I want you to save all my plots there. I want you to save all my output or data sets there. I want to read in data sets from that directory as well, right? So setting the working directory is an important part of that process. So how do we do that? Well, we could just highlight this and paste it over into our window, right? The way the function works is it says set WD, and then within where it says directory, we just replace it with the name of our directory, right? So we're gonna remove that because we need to tell it where exactly we're gonna be going. We can see down here in the console window though, there's no directory listed, or rather it's in my home directory, right? How do I know I'm in my home directory? Well, the files that list there are in my home directory, right? So to change the directory, what we have to do is, on a Mac, we go to whatever folder we want. I'm gonna right click, instead of copy PA606, which is my folder that I want to, save as my directory, I'm gonna hold down Option, and it says, instead of copy PA606, it says copy PA606 as path name. So I'm gonna copy that, bring it back down here, and then paste that there. So now I have go into my users folder, and then inside users go to Burl Van Jr. Into Burl Van Jr. go to my desktop, and then into my on my desktop go to PA606. Right. So I can do that and save my working directory. I won't run it now because I want to show you an easier way of doing it. The easier way of doing this is by going to our session menu, highlighting set working directory, and then selecting choose directory, right? And then we can sort of navigate through the directories to figure out which folder we want to use. So let's do that. Instead of this, I'm gonna go session, set working directory, choose directory, right? So I'm going to the session menu, highlighting set working directory, and then highlighting choose directory. I'm going to click on choose directory, and then it's going to tell me, where do you want to go? Right now you're in your home directory. Where do you want to go? So I'm going to go to my desktop. I'm going to go to PA606, and I'm going to select open. Wow, what happened there? So now we have a set working directory code that's listed there. If you look here now, in my console window, instead of just a tilde there, it says tilde/desktop/PA606. So it changed from a tilde to a new directory. Here we can see we're no longer in home, we're in home desktop PA606. So that's exactly what this means. On a Mac, oftentimes you have the set working directory. You have this tilde means users / whatever your username is / and then everything after that is the name of the directory that you're in, right? So tilde means user / whatever your username is. So I can just take that, copy it there, and run this. So let me clear this window. To clear a window, you highlight Control L, or click on Control plus L, and it's going to clear that bottom window. So I'm going to rerun this. Look, no error, and I'm still in desktop PA606. The difference is, for a PC, you're going to go into whatever folder that you want. If you wanted to type it out like I listed previously, where this was directory and you just pasted in your path name. To get the path name, you'd right click on a folder or a directory, get the location, paste that location in there, but then also you have to add the name of the directory because it's not going to list it in that location, right? So even if I say, give me the location of PA606, it's going to give you users Burl Van Jr. desktop, not necessarily the name of the directory that you want. So you'd have to add that in, and then beyond that, in a PC, we have C drive, colon, // users / username / desktop / PA606. First off, R relies on forward slashes. So you're going to have to go in and change all those backslashes to forward slashes. Second, it's not going to list that directory like I mentioned. So you're going to have to add that directory in, right? So I think the easier way of doing it is the latter way that I showed you, which is set working directory, choose directory, I choose PA606, and I'm good, right? And you can, again, like I showed you before, you can copy and paste this over. Right, so I'm going to clear this, Control L. There we go. All right, installing and using packages as libraries. So I mentioned before that R tries to remain lightweight. And to remain lightweight, it has to rely on packages in the cloud, right? So it doesn't create this bulky software that you download immediately. It creates a lightweight software platform that you can use immediately. But if you need cool, interesting little features to add to your program, then you have to install those features, and they're known as packages. So to install packages, you use this function called install.packages. I know, crazy, right? So you highlight all of this. For this exercise, we're going to be using the mass package, the psych package, the lattice package, and the mosaic package. So we highlight all of those. Those are 4 lines of code. We can hit enter and paste that in, and then we go ahead and install those packages. So it should look something like this. And now those packages are installed. How do we know? Well, we get to the end. There's no more, red text that's saying, hey, we're trying this URL to install this package. We get to the end, we have a blue caret and a blinking cursor. That means we're good. So those packages were installed. Great. The important part to remember, though, is that when you install a package, once you've installed it, you never have to install it again. Even if the package is updated, when you try to load that package, it'll say, hey, you need to update this package so we can make sure you have all the functionality. So once you've downloaded and installed, you never have to do it again. So knowing that, we're just going to delete all of this. Right? We don't have to install it again. So now we have a local version of each package on our machines. They're not being used right now, but they're local copies. They're really small versions though, right? Next, because we only have them on our machines and we're not actually using them yet, we have to tell R, hey, use these packages. So to do it, instead of load packages or read packages or something like that, R uses this function called library. So we read all of our packages as libraries. So I'll go ahead and copy and paste from the website. If you're not copying and pasting from the website yet, I would highly suggest that you do. It's easier to do it that way. So now I have these 4 packages. I'm going to highlight them and select run. A good keyboard shortcut though that I did before was, instead of hitting run, hitting command enter on a Mac or control enter on a PC. So I'm gonna run those, and look, all of those loaded. I tried to load them again, nothing happened. It just said, hey, we already have those loaded. So unlike install.packages where you only have to do it once and then you can delete those lines of code from your script, for R, or for loading the packages, we have to always call them, right? We always have to call the library. All right. You'll notice I've been running things and they appear down here. Sort of a refresher, right? Up here, we just have a script window where we have a bunch of text, and that isn't necessarily running anything, right? I hit enter here, nothing happens, right? I hit enter here, nothing happens. However, we have to run those and send them to the console window below. The console window is base R actually running these things. All right. Next, I have a brief note on commenting. Throughout any script window, you'll notice that you'll see a line of text with a pound sign or a hashtag preceding it. This is what we call a comment. It's just a note to yourself, and it's what it does is it says, hey, this is what's going on at this point. It's a reminder for you to figure out what's going on in the code below. The way that R reads it is that it shouldn't be a line of code, right? So anytime you put a pound sign in front of text, it'll actually turn it this green color, and then R will treat it as nothing. It'll treat it as just text, right? So let's say I wanted to make a comment for myself, and I say, this is how you load packages. So I'm gonna highlight that and run it. Whoa, error. Unexpected symbol in this is. So right now, what R is trying to do is figure out what this is means. It's trying to figure out what kind of code is this. It's not treating it as a comment to ourselves. So to treat it as a comment, we go, put a hashtag right in front, and we see that it turned green, right? So now it's a comment. Now, when we run this, so I click run or hit Command Enter, what happens? R just says nothing, right? It says, oh, this is just a comment. Don't read it as any code, right? Don't throw any errors because this is just a comment to the researcher. Okay. Cool, now we know how to comment. Next, we're going to be working with data. So because this is an object-oriented programming language, we can do a bunch of different things. First, I want to show you how to make general calculations. So let's say, I'm going to throw another comment, make calculations. Let's say I wanted to do 3 plus 2, then 5 minus 1, then let's see, 8 times 3, and 9 divided by 4, right? So here, this is how we specify different calculations in R, right? We have the plus, the addition, subtraction, multiplication, division, right? So I'm going to highlight this and run it, right? Because when I hit enter, we didn't see it populate down here, right? So I'm going to highlight this and run it. 3 plus 2, response is 5. 5 minus 1 is 4. For multiplication, we use the asterisk. So I'm going to hit Command Enter. 8 times 3 is 24. And then 9 divided by 4 is 2.25. Right? So it's easy to make these calculations. It's great. Right? However, in R, because it's object-oriented programming, we can do a bunch of different things. And the most important thing that we can do is what we call the assignment operator. Right? Or the thing that we can use is the assignment operator. When we use the assignment operator, what we're doing is assigning object names to any calculation or any data set that we're working with, right? So what this does is it creates a working copy in R's memory that we can use at a later time. But we have to assign it a name, a new object name, using the assignment operator known as the left arrow. Okay? So we do it like this. The new object name, a left arrow pointing at the new object name, and then the calculation or the data set that we want on the right hand side, right? So you point to the new object name. So this works for any data set or any calculation, right? So here we see what we're doing is making the calculation of 3 plus 2, but then we're doing that calculation and throwing it into the new object called x, right? So let's do that. Let's highlight that. 3 plus 2 is x. Assign. So what's going to happen? I run 3 plus 2 by itself. It's going to run a calculation, right? I run this whole line, what happens? I want you to keep an eye out for the global environment up here. I run this. Okay, it didn't give me the calculation. What happened? Oh, but I look up here, now we see x under values, and it equals 5, right? So what it did was it created an object in our global environment called 5, right? It created the calculation. So now, if I type x here in our console, meaning it's not up here, it's not going to be saved, hit enter, I have 5, right? Now what can we do with that? What happens if we say x plus 2? Is it just going to say x plus 2? No, it's going to say 7. So now we have we can start thinking about these as variables, right? Now we have a variable that we can use and create calculations or manipulations on that same variable. We can say x divided by 3.5, right? 1.428571, right? That's great. Let's say I have a variable, so I'm going to clear this. Those are just examples. Let's say I have a variable called mean. And let's say I said the mean for this calculation is 7. And the standard deviation is 3. Right? So now we have mean and standard deviation. That's great, right? That's sort of one way that we can start investigating the relationship between, other calculations like confidence intervals, confidence levels, z-scores, things like that. Right? So we can just throw them in that way. Let me clear this out. So we have x. Quick reminder, removing objects from your environment. Sometimes you're going to be working with a bunch of different objects and you're going to figure out that you don't need any of those objects anymore. And to remove them, we use this line of code, rm, and then the name of the object, right? Rm and the name of the object. So we'll do that here. Remove x. Say rm and then x. Rm mean and then rm sd. So it's going to remove everything in my environment now. So now everything's gone. SD mean. All right. Reading in data sets. As researchers, oftentimes what we're going to be dealing with is reading in a CSV file, right? And we know that a CSV file is sort of an Excel spreadsheet with a bunch of information where the rows represent the number of observations, right? The rows are each observation exists on a row, and each variable exists on the column, right? So we're going to read those in, but we have to figure out how to actually read those in, right? And we have this nice function in R called read.csv, and it tells it, hey, if there's a CSV, I want you to read it in. So this function here, we say read.csv, and inside the parentheses we have pathname.csv. So what that does is it needs to be replaced with the actual path to the CSV file, right? So you can right click on a CSV file, get the path name, and then copy and paste that in, right? Header equals true, right? So oftentimes when you have an Excel spreadsheet, you'll have observations on the rows, but variables on the columns. And when you have the variables on the columns, oftentimes you're going to have variable names listed on the first row, right? The first row would be variable 1. This is the name of that variable. variable 2 listed here, variable 3, right? So what we call that in R, or anytime you're working with a CSV, is a header, right? A header is going to tell you the variable names for each observation, right? So if you have one of those, if you have a header row, then say header equals true. Sometimes you're going to run into the situation where you have a data set with no header, meaning it has no variable names. So you would change that to header equals false or header equals F. And when you do that, you can read in the data set, but it also means that you're going to have to go through and sort of physically figure out which variables are which. Then finally, the last argument within the read.csv function is sep equals comma, right? So sep, separator. Sep stands for separator, and we know that we're reading in a CSV file, which is a comma separated value file, right? Comma separated. So we say our separator is a comma. Sometimes when we read in a file, it's tab delimited. So it's going to be a tab delimited file. And we would change it to a tab, right? Just highlight that and replace it with a tab. So click tab. But most times when you're reading in a CSV, it's going to be a CSV or a comma separated file. So the only thing you really need to replace here then is the path name. Here we see, whoa, it's not just the read.csv function. You call something data1 and you're pointing to it. Oh, wait. That's the assignment operator. So what I'm doing here is instead of just reading in that CSV file, instead I'm saying, hey, read it in, but give it this new name, this object name of data1. So what should happen is I should read in this file and it should populate in my environment as data1. So let's go ahead and copy and paste this over. So I'm gonna copy this. Read in a data set from CSV. I'm going to copy that over. So I have data1, but I don't have a real data set. So let's go ahead and find a real data set on my computer. Okay, so now we're going to read in this data set. So we have to locate this data set on our computer. I have this cars data set. I'm going to right click, option, cars.csv, path name, and I'm going to just paste that in. You see that copy and pasting the path name came in handy. So I'm gonna run this, and what should happen is that nothing will populate down here, right? It'll just say the same line of code that we listed here, but we should get a data set called data1 up there on the right. And that happened. All right, so now we have a data set. Cool, it's all listed here. Looks very familiar to other data sets we've worked with. All right, now, sometimes for at least the first portfolio that we're going to be doing, we're going to be working with stock data sets in R. And I mentioned before that every package that's built in R comes with a stock data set, right? They have to, when you build a package, you have to provide a data set for other R users to use to test out your package. Right? So within the mass package, we have the car manufacturer's data set called MT cars. To use this, all we have to do is call it, right? Because we've already loaded the mass package, all we have to do is call MT cars. So let's just call MT cars. Let's say call MT cars data set, right? So I'm going to say MT cars. So I'll run this, and now look at this. We have a bunch of different observations. We have MPG, cylinder, displacement, horsepower, all of this information about cars, right? I'm not sure what this data set is. I mean, I know what it is, so we can figure out information about it any data set that we have or any function that we're interested in by using this line of code. Question mark, and then whatever you want to add in. So question mark, empty cars. Oh, look what happened. We moved over to the help window, and now we have the empty cars data sets listed here, right? So we have 32 observations with 11 numeric variables. MPG represents miles per gallon. Cylinders, the number of cylinders. Disp is displacement. Horsepower, rear axle ratio, weight, quarter mile time. Engine, is it V-shaped or straight? The transmission, is it automatic or manual? Number of forward gears, number of carburetors, right? So we have all of this information here. So again, you want to figure out any information about a function or a data set, you type in a question mark and then that function name or that data set name. So we were able to figure that out. I'm going to clear this again. The important thing to remember though is when I read empty cars into the console window, I can't really do anything with it, right? I can't really do anything with it. It's because it's an image of a data set. What happens when I want to use the data set? Can I run the mean for a variable, the standard deviation? Probably, but we don't have our own copy to be working from. We have a cloud copy. What happens if that cloud copy is removed or it's changed? Well, we need to create our own copy. So instead of just calling it, we're going to say create an object out of empty cars data. So we have that. Instead of that, we're going to say create an object called data1. Wait, we already have an object called data1. Well, what's going to happen here? Once we do this, our data1, since it already exists up there, when we run this, it's going to overwrite whatever exists there. So let's do that. Now, data1 has 20 observations. We look again, we run this. Now it has 32 observations. What that means is whatever data1 was before, it was able to overwrite everything there. All right, so now we look at it, and it looks exactly like the data set below, right? 21, 21, 21, 21, 22, 22, 21, 21, 40, yeah, right? So it's matching up. So we have that. If we want to call, so we should be clear on all of that. We've created a new object called data1, and it appears in our environment window. Let's say we wanted to call information for one variable within that data set. Well, to call a variable from within a data set, we need to use another operator. Right? This time, we use the $ operator. Right? And this helps us call up a specific variable from within an object or from within a data set. So it operates like this. Data set or object name, $, whatever the variable is. So if I wanted to call the MPG variable from the data1 data set, I would say call MPG variable from data1 data set. I'll say data1 object. I can't just say MPG, right? What if I wanted to call the displacement variable from the empty cars dataset object? I would say disp, right? Wrong. Right? Disp not found. To do that, we have to use the $ operator. We have to tell it, hey, there's a data set called, or an object called data1, and inside that object, $, whoa, look, all of these options pop up, right? So every variable that exists in that data set populates here because it's saying you selected a data set or an object, and now you're telling me that you want something from within that object. So I can select disp, select this, and what will happen is it's going to list all the values that exist, right? This is the first value. How do we tell? Because it says 1. This is the 17th value, right? Anything in brackets to the left lists the number or observation that you're at, right? So first, second, third, fourth, fifth, 6th, 7th, 8th, 9, 10, 11, 12, 13, 14, 15, 16th, 17, 18, 19, 20, 21, 22, 23, right? All the way through the 32nd observation. What if we wanted MPG? We say data1 MPG. Run that, and there we go, right? 21, 21, 22.8, 21.4. Wow, how do we check that? Well, easy way of checking it is, luckily we're using RStudio. When you have RStudio, you can go over to your global environment, look at the name of the dataset. Don't click on the plus sign or the play sign. Click on the name of the dataset. You click on that, and it'll populate something that looks like an Excel spreadsheet, right? It's going to list all the variables and all the observations that exist in your dataset, right? So we just called data1.mpg or $.mpg. So the first observation for mpg should have 21. mpg 21. Second, 21. 21. Third, 21. 22.8. Third, 22.8. Fourth, 21.4, 21.4, right? So now we see that all of these match up. What about DISP? 160, 160, 108, 160, 160, 108, right? So these are matching up. So I'm going to close this. Everything fits. Great. Now, we're going to move on to univariate statistics. Univariate statistics are things like mean, median, mode, standard deviation range, sometimes variance, right? We can also get skewness and kurtosis. Right? The stock R program comes with summary as a function, but it doesn't provide a lot of the measures. So instead, we're going to use the describe function from the psych package, right? So to describe or give univariate statistics for all the variables in one data set, we can use, so I'm going to say get univariate stats from all variables in data1 data set. I'm going to say describe data1. Okay, I'm going to clear this. And what we get here is a list of each variable, right? MPG variable, cylinder variable, disp variable, right? We have the number variable, right? There are 11 variables. We have 1 through 11. It says the number of cases that responded to each of these variables. The means for each of those variables, the mean for MPG is 20.09, the standard deviation is 6.03, the median is 19.2, right? We have min, max, range, skewness, kurtosis, right? All of that is listed. If we wanted to get univariate statistics for every, or for one variable, let's say we want to use the MPG variable in the data1 data set, we do the same thing we did up here. We have to call a specific variable from within that object, within that data set. So instead of calling data1, we say data1 $MPG. Look, it populates there. So now I'm going to clear this and run this. Wait, that looks the same as what we saw before. The mean for MPG is 20.09. The standard deviation is 6.023. Median 19.2, right? All of these look the same. You can do this for every variable. Let's compare that again to the full data set, and we see MPG 32, 32, mean is 20.09, 20.09, 6.03, 6.03, right? It's matching up. Great. It works. I also have a description here on how to call univariate statistics broken out by categories of another variable. We use the describe by function. So when we start getting into things like bivariate statistics, this is going to come in handy. Let's say we wanted to break down MPG based on the number of cylinders in a car, right? So we would use this describe by function. So I'm going to say, let's say instead of calling descriptives by one variable or by the whole data set, we're going to say descriptives broken for MPG broken out by number of cylinders in a car. So I'm going to paste that. So instead of the describe function, we now have the describe by, which is a function within the psych package. So we have describe by. I'm going to run that. Now we see we have group 4, meaning a 4-cylinder car, right? So it breaks down by group. So we say broken out by number of cylinders. So this one's going to be the grouping variable, cylinders. It's the second command. The first command is going to be the thing you want the mean for, or the univariate statistics for, okay? So we have the first group, which is 4-cylinder cars. The mean MPG is 26. For 6-cylinder cars, the mean MPG is 19. For 8-cylinder cars, the mean MPG is 15. So we see that, at least while right now we're only looking at univariate stuff, and this is just sort of a stepping stone towards investigating bivariate relationships, we can see here that as the number of cylinders goes up, fuel economy, or MPG, goes down, right? So we have higher fuel economy at 4 cylinders than we do at 8 cylinders, right? So it goes, mean is here, it goes down for 6 cylinders, it goes further down for 8 cylinders, right? So that's just an example to get us started looking at bivariate relationships. Next, I do want to talk about a brief note on skewness and kurtosis. So skewness is a measure of how close or far that distribution is to the normal curve. It measures the clustering of scores along the x-axis. Kurtosis, on the other hand, is a measure of peakedness, right? How high or low that distribution is relative to on the y-axis, right? So what they're trying to figure out is how far from mesokurtic this distribution is, and the normal curve is mesokurtic. So skewness, in particular, ranges from negative infinity to positive infinity, right? The sign indicates the type of skew. So a negative number represents negative skewness. Positive number indicates positive skewness. 0 indicates no skew, which is the normal curve. But we do have some cutoffs. So I say greater than the absolute value of 1. So if you have a value that is greater than positive 1 or greater than negative 1, right? So it's negative 1.2 or 1.2, that's going to be high skewness, right? So these things are very skewed. And again, the sign represents whether it's negative or positive skewness. Moderate skewness ranges from 0.5 to about 1, right? So negative 0.5 to negative 1, and then positive 0.5 to positive 1, right? And this is what we call moderate skewness. And then low skewness ranges from 0 skewness to 0.5 skewness. So it's in absolute value. So it's 0 to positive 0.5 or 0 to negative 0.5. So those are the cutoffs. Usually we want to see something in the low range. Because a lot of these future tests are based on it, and all of these future tests are going to be based on assuming that we're dealing with a normal curve, we want to find that the skewness for our distributions is going to be low, right? Between 0 and negative 0.5 or 0 and positive 0.5. But oftentimes, as researchers, we're willing to accept a moderate skew, right? Between 0.5 and 1 absolute value. Anything beyond positive 1 or negative 1, so more than that, that's going to be too high of skew to assume that it is going to be a normal curve, right? So with low and moderate skewness, we can assume normality, right? It looks close enough to normal that we can't say that it's significantly different than a normal curve. But high is definitely going to be significantly different. So we want to keep that in mind when we start running these tests. If we don't meet the assumption of normality, then we can't run specific tests. All right, and we also have a measure of kurtosis. And kurtosis, originally it ranges from 1 to positive infinity, but we have an adjustment called excess kurtosis that ranges from -2 to positive infinity. So we know that negative values usually represent platykurtic distributions, so flatter distributions. Positive values oftentimes indicate leptokurtic distributions, but distributions that are close to the value of 0 are mesokurtic. So we have the range from -2 to 0. That's going to be a platykurtic distribution. Anything between 0 and 1 is going to be considered mesokurtic, so it is a positive value, but it's between 0 and 1. And then anything from positive 1 to positive infinity is going to be a leptokurtic distribution, right? So we want to make sure that we're somewhere in the range of 0 to 1. If we're like -0.5, so it'd still be a platykurtic distribution, but it's close enough to a normal distribution that we don't have to worry. Anything that's close to -2, or usually, +2 through positive infinity, those are going to be really outside the bounds of being a normal distribution. So we want to consider, should we really be running this test that's based on the assumptions of a normality? I have some descriptions here if you want to run specific univariate statistics. To run the mean, we say mean, and then the variable, and then na.rm equals true, or t. na.rm equals true means if you have missing data, we still want you to calculate the mean or the median or the standard deviation, right? Oftentimes, R will treat missing data as either infinity or 0. And when it does that, that can balloon the mean or really shrink the mean. So to accommodate for that, it says, well, we don't know, so we're not going to give you a value. To fix it, you just say, add this option of na.rm equals true. So it's going to remove, right? It means remove all the missing cases, or remove all the NAs, remove all the missings. All right, assessing normality. We're wrapping up here. When we assess normality, we can do it by visualizing data. So we can assess normality looking at the skewness and kurtosis statistics, right? So we'll go back up here. We do have skewness and kurtosis statistics using the describe function. So let's go describe MPG. Let's describe all the data. We have skewness and kurtosis here. Skew, right? Skewness ranges from -infinity to positive infinity, and we want something that's between 0 and 0.5. Absolute value, we see this is 0.6, right? So that's a moderate level of skew, right? It's above 0.5, so it's moderate skew, but usually we can look at these variables and figure out, hey, that's close enough to, low or moderate. The skewness is not too much, right? Negative, that's a negative skew, but it's very low, between 0 and 0.5. Low, moderate, low, moderate, and here for carburetor we have high skew, right? So for this one, we would say that one's so far from normality that we should probably not use a normal distribution, or assume that this is a normal distribution. And because of that, this variable can't be used for bivariate analyses. We also have kurtosis, right? We have negative, it ranged from -2 to positive infinity. Negative skew or negative kurtosis means that it's platykurtic, right? So this is platykurtic, 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 platykurtic. This one's very close to 2, so we would say that's too far from a normal curve to assume that it's mesokurtic. So we can't really do normal distribution kinds of things with the cylinder variable. But for all other, and same here, right? Although it's closer to 1 than it is to 2, so we may make that assumption. But all of these seem like the kurtosis isn't that bad, right? This is leptokurtic a little bit. This one's very leptokurtic, right? This carburetor one is both highly skewed and highly leptokurtic, so we should probably not use that variable. This one's also this one's platykurtic. Right? This one's highly platykurtic, VS, highly platykurtic, so we should probably not use that variable for analyses. But we can also visualize these things, and to do that, we can use a bunch of different tests. So we can look at histograms, we can look at box and whisker plots, and we can also look at normal QQ plots. So we have the histogram. We can run a histogram on any variable. We can do it using the hist function, right? Hist dataset or object name, $ variable name. So we can run histogram on that. Let's do comment histogram for MPG variable and data1 data set. We run that and look, it populates in our plot window. So we see the histogram here. This histogram looks like it has a positive skew, right? It does, because when we look at if we were to plot a curve over these, we could see that the tail is going to extend to the right. And we look at the skewness here, and the skewness is positive. Great, we were right. We also see that it's sort of platykurtic, right? So it's not as high as one would expect for these data. It's sort of flatter than one would expect, right? So it's sort of platykurtic. So that's plotting a histogram. We can look at it and assume whether or not it fits normality. For a histogram, we can also use this other function from the lattice package called histogram. So instead of hist, we have histogram. So I'm going to say plot histogram using histogram function. So this one will look a lot the same, right? We say whatever the outcome variable is, the thing we're interested in, it's MPG. You'll notice here we don't have to say data1 $MPG. We just say tilde MPG, and why do we do that? It's because we can specify the dataset name or the object name. So we're saying MPG is coming from the dataset called data1. Main, that argument is to create a title for the plot, right? So instead of, histogram of data1 $MPG, I'm saying histogram of miles per gallon. And then type is count. So that last argument says, give me the frequency and not the density. I'm going to run that. And stock in this package, we have the blue coloring, right? The cyan coloring or cyan coloring. So we see this. It still looks very similar to the last distribution, right? It's a positive distribution, positive skew. Right? We see MPG is broken down here. We see the count or frequency on the y-axis. Next, I want you to do the same thing, but now I want to overlay a density function as well as the mean, right? So I'm going to plot the mean line as well as a normal curve to to see, does it really fit a normal curve or not? I'm going to say paste that. I'm going to say plot histogram using the histogram function, overlay mean and distribution. And then, so we have the distribution listed, right? So we have this density function. I'm going to run that. And now we have the same distribution, but instead we're including the mean as well as the normal curve. All right, so we have that. Next, we can also, so in the future we're going to take steps to break down these histograms. So right now we've plotted one histogram for all the data, overlaid a normal curve and the mean. But in the future, this histogram function also allows us to break it down by various other variables, so we can look at bivariate relationships. So we see here, I've created a histogram of MPG, but I say break it down. That line indicates break it down by cylinder, right? Still the data one data set count, and histogram name, I give it there. Right? So we have that. So we see that for the histogram for 4-cylinder cars, we see it's pushed up towards the top, so we see higher MPG, we see middle range MPG, and then we see low MPG for 8-cylinder cars. Right? Next, we have a box and whisker plot. The box and whisker plot is important because it allows us to see whether or not the distribution itself is normal, right? So to do that, what we do is we use this BW plot function from the lattice package. And what it does is it will give us the box and whisker plot for that variable. The box and whisker plot itself has a bunch of different breakdowns. So let's look. The bottom or left end of the whisker represents the minimum score for that variable. So it plots the minimum score for us. The bottom or left end of the box, so like bottom left end of the whisker represents the minimum score. Top or right end of the whisker represents the maximum score. So we have min and max, right? The box represents 50% of the cases, right? So what this is saying is that the bottom end line represents the 25th percentile case, right? The first quartile. The middle line, sometimes represented as a dot, represents the median, right? The 50th percentile. The top end or right end of the box represents the 75th percentile, right? So we have 25th, 50th, median, 75th, right? So it says, what are the middle 50% of cases fall? Where do they fall? That's the minimum, that's the maximum. Finally, I say dots outside of this minimum maximum represent outliers, right? So we know what outliers are. Outliers are cases that don't necessarily fit within the distribution. So those will be listed there. To plot a box and whisker plot, we use this function, the BW plot function. Here we see the same thing. MPG is going to be the outcome, the variable we're interested in. We don't say data1 $MPG. We just say data equals data1, right? And so we specify the MPG there. PCH just says, do you want the dot or do you want a line in the middle of the distribution for the median? For most plots, you want to see that line instead of the dot. So I said, give me a line. So PCH is a line, and then main is give me the box and whisker plot of MPG. So that's just a name you can give to that plot. So you can change it based on the variable you're using. So I'm going to say plot box plot or box and whisker plot of MPG. I'm gonna do that. That should also populate there, and we see that. So generally when we're looking at the box and whisker plot, what we want to figure out is, does it look normal? And how do we know if it looks normal? Well, generally what we want to see is the 50th percentile. We want it to be close enough to the center between the minimum score and the maximum score. Right now, this doesn't look exactly close to the center, but it looks close enough. So what you'll learn with all these visual depictions is that, okay, it looks close enough to normal, right? It looks close enough to mesokurtic. It looks close enough to skew, normally distributed and not skewed. This one looks close enough to being at the center of the distribution, right? We know that it's a little bit off to the left a little bit, meaning that we're going to have most of the cases here and then a few cases over to the right, but generally it looks like it's sort of normally distributed. We also want to see that the median line, the 50th percentile falls generally in the middle between the 25th percentile and the 75th percentile, between the bottom end of the box and the middle of the box, or the end of the box. We don't want to see something where the median falls right smack dab near the lower end of the box or the top end of the box, right? So if I had to assess this, I say, well, it's slightly positively skewed, right? We can tell it's positively skewed. If we plotted this, we say 50% of the cases fall here, and then it sort of dips off toward the end. While it's positively skewed, we can assume normality because it's not that skewed, right? This is here, it's right in the middle, and it's not too far off from the middle of that box. In the future, we can also use that same BW plot function to break down by group, right? So we have this example here. Instead of just looking at MPG, we're also looking at MPG broken down by the number of cylinders. So we have 4-cylinder cars, we have 6-cylinder cars, we have 8-cylinder cars. So we see 4-cylinder cars are clustered around the top end of MPG. 6-cylinder cars are really close. They're really bunched up. And then 8-cylinder cars are sort of more bunched up here. But then we have an outlier down here. All right, and finally, we have the normal quantile plot. And the QQ plot, or quantile plot, is a visual representation of an empirical distribution, so the data we have, and we fit that to a theoretical distribution, right? A theoretical distribution meaning if this MPG variable, or if this variable were normal, this is what the score should look like, right? So we fit our data against the theoretical data that should occur based on a normal distribution. So I said, if I took these data from a normal distribution, this is what it should look like. So based on this plot, we say, if our data actually fit a normal curve, then the dots that appear on this plot should follow a straight line or fall directly on this straight line, right? Yeah, so we can do that. I have a QQ plot here of MPG. This should change not from wr.hand, but to MPG. So I'm going to copy this over. So we say plot, I'll say plot QQ for MPG. And we say that we have this function xqqmath. So it's based on MPG. It says it's coming from the data1 data set. We have fit line equals true, meaning draw that line. That is the line where if all data are coming from a normal curve, it should be on that line. And then normal QQ plot, this main is again the title, so I'm going to place this with MPG. And it said expected normal. So all you have to change here is the name of the variable. And again, if you wanted to break this out, you would just do the next variable that you wanted, right? So say MPG, I'm gonna run this, and there we have it. So we have a normal QQ plot of MPG. So if every empirical observation fit a normal curve, then every observation should be on that line that's drawn. Does every dot fit that line? No, right? But are they far enough to assume that this is not a normal curve? Again, I would say no. So what we're really looking for is, generally, do these dots follow that line, right? We see a little dip here under and then a dip over. That's usually not a good characteristic, but they're so close to the line that we can assume that it's generally a normal curve. If they were way out here above the line and then they curved under and then curved way back up, then we would say, okay, that's too far from normality. But because generally these are sort of close, right? Again, this is sort of subjective looking at these data to assume normality. But when we look at it, we can say there's no trend that looks so different from that normal plot. So we assume normality. All right, well, that's all I have for you today. Again, we can break that down. I show that here, but that's all I have for you, and that should set you up to prepare for the portfolios that we have both this week and in the coming weeks.